Okay, guys, back. This should finish her off. All right, propose a feasible chemical for the salt bridge. So we're gonna want to use the spectator ion and an alkali of the spectator ion. So our spectator ion, according to the battery above, who's our spectator ion here? Nitrate. Yay! I love it when nitrate is. So we're gonna pick an alkali like K plus and nitrate. So potassium nitrate would be a nice chemical for our cute little salt bridge. What would happen if the salt bridge would removed? Voltage would go to 0 volts. Oh, so sad. You might have remembered that from the lab when I had you remove the salt bridge. Okay, here we go. 5. Atomic radius of radium is smaller than that of francium. Alright, so we got a horizontal relationship. Okay, so why? Francium has 1 more proton in its nucleus that pulls on outer electrons harder. Therefore, it's smaller. Okay. pH 3 is polar, while pH 5 is nonpolar. That's what pH 3 is going to look like. That's what pH 5 is going to look like. Okay. So pH 3 has a lone pair on central atom that creates an asymmetric shape. The boiling point of ethanol is 70 degrees, while that of dimethyl ether is 59 degrees. So if you do the whole structure for ethanol, okay, you're going to end up with a CHHOH. Okay, that is an H bond. So this is polar because as long as there's one polar central atom, the whole thing is polar with H bond. And dimethyl ether, you're going to end up with a structure that looks like this. Now, although it is polar with no H bond. So basically, what's going on here is ethanol has stronger intermolecular forces. So fluorine has a larger first ionization energy than that of chlorine. Ionization energy is how hard it is to remove an electron. Okay? So this is a vertical relationship. So fluorine's valence electrons are in the second energy level, while chlorines are in the third. Therefore, fluorines are less shielded from the nucleus, making the ionization energy larger. Yay. Alright. E. Ethine has a shorter CC bond than ethene. So ethine looks like this. Ethene looks like this. Okay, so the extra pi bond in ethine shortens the CC length, and it actually subsequently, and it increases the bond energy. Alright, next one. Here we go. Ooh, yes. Answer the phone. We're almost done, guys. So, draw little structures. Now, what I want you to do on this one is see multiple choice. We had to do that, and I believe it was, which multiple choice was it? When was it, goes? Okay, 26. See multiple choice number 26. I believe that's vodcast number 2. So you're going to end up with a real structure that looks like this. So that, and because you could have made the double bond in any location, resonance is going to exist. And because there are a lot of people who missed the O3 problem, let me just emphasize that that means that is diluted across both. You can think about it that way. Okay, and that's SO2. And we all know that our good friend carbon dioxide, looking like so. Indicate the shape of SO2. There's 3 things around it, so that's sp2. There's 2 things around it, that's sp. The shape of this is bent. It's one of the 2 types of bents. You can have 2 things, 2 letters, and 1 lone pair, 2 letters and 2 lone pairs. Sp in this case is going to be linear. How many sigma and pi bonds are present in carbon dioxide? Okay, 2 sigma. That's a signal. That's a single for sigma. 2 pi. That is pi. Explain the difference in polarity. Alright, so if you look at SO2 versus CO2, okay, SO2 has a lone pair that creates a polar / asymmetric geometric shape. Alright. Which molecule would be most likely to found in the gas phase? Okay, so if you look at the sticky chart, SO2 is going to be here. That's dip. And CO2 is going to be here. Right, almost done. That's linear. We know that this tends to be solid. That's liquid, and there's a gas. So SO2, CO2, due to weak intermolecular attractions. All done, yay!